Dr. Johnson received his doctorate of physical therapy degree from Bellarmine in 2004. And then after he graduated, he worked at Cardinal Hill as a physical therapist for
just under 2 years.
yeah, I always say a year and a half, so I thought it was about 2 years. And then, you know, since he needed not only DPT behind his name, he wanted PhD behind his name, he came back to UK and got a doctorate in neuroanatomy, or anatomy and neurobiology, excuse me. He has served many hats, from teaching in medical school. He's taught gross, but he is now a faculty member in physical therapy. He's a K Award winner for some of his work. What more can I say? He's the man, the legend. Without further ado, thank you, Dr. Johnson.
Thanks, Joey. And thank you all for having me. So, quick announcement first. So I've been sick the last couple of weeks, so if I have any cognitive brain fog moments, please excuse me. I haven't been able to hit the gym recently. So whenever I give talks publicly at conferences, inevitably at the end of the presentation, a lot of people ask me, well, yeah, great, we know exercise is important for health. How do we motivate people to exercise? So I want you all to be thinking about that as I show you all some of this data, because that's something that I'm thinking about getting into. And it's always amazing to me how people just choose not to exercise. So this is me at Jalapenos, and this guy has his Fitbit right here, and he's getting his steps. So he's cheating somebody, more importantly himself. But I know that there are some scenarios these days where you can actually, if you lose so much weight, they'll pay you. I don't know if this guy's participating in anything like that, but I was getting a carry out at the bar, and I was looking down, I was like, what's he doing? He's playing his Fitbit this over and over again. So he had his margarita and his chips. Cheating so much. So be thinking about that. You know, I know you all are studying this, but how do we motivate people to exercise? You know, it's either somebody that really enjoys it, like myself, so I have addictive tendencies when it comes to this. I mean, you can't tell, I'm more of an aerobic endurance athlete, but versus those people that I've dated in the past, people in my family that just refuse to exercise. So it's this dichotomy is interesting to me. So what I'm going to primarily talk about today is the aging brain, because that's what I'm interested in. And I'm also interested in it because we're all aging, right? I'm aging, so how can I help to preserve my brain tissue? And we know that aging is this universal phenomenon, right? But this is what NIH cares about here, that we're going to have a large number of individuals that are over the age of 65 by 2050. Okay, so when you're submitting grant proposals, you got to give the NIH some numbers. But it's important to all of us, right? Because we're all aging. How can we take care of our bodies to help preserve both cognition and physical function as we age? So I'm primarily interested in how we preserve the brain as we get older. And so we see, if we look at the literature, this is actually my brain several years ago. It's pretty pristine. Look how small those ventricles are there. This isn't a cross-sectional representation, or this is a cross-sectional representation. This is not a longitudinal representation of what happens to your brain as you get older. But if you look at an individual that's 33, so this is a sagittal slice through the head. So it's cut this way, and you're looking to the right side of the brain. Here's the nose would be in the front. If you look at the difference here, you can see a significant increase in the size of the ventricles, and you see some atrophy along the outer edge of the brain itself. And this is pretty typical. Again, even though this isn't representing a longitudinal relationship, this isn't the same person, this is typically what we see when we look at longitudinal studies. So how do we preserve brain tissue as we get older? And so this is a macrostructural representation of what we see with aging. And so what we see, if you look at the evidence, we see that brain health shows a positive relationship with physical activity or exercise or cardiorespiratory fitness. Insert anything here on the x-axis. And this was the literature that was out when I started, particularly this Kramer paper in '99 that was out when I started my PhD. So we we already knew that this relationship was there, this positive relationship between brain health, cognition and structure, and cardiorespiratory fitness, or just fitness overall. And so, coming into the PhD program here, we had an MRI technique that we'll talk about called diffusion tensor imaging, which allows you to look at the microstructural integrity of the brain. So what I just showed you with that gross picture with an enlargement of the ventricles was a macrostructural image. And so this MRI technique allows us to look at the microstructural integrity of the brain. So really what we're looking at is we're looking at bundles of axons, okay? Those projections from the neuron cell body to some other neuron. And what we see here is aging, just like we saw with macrostructural integrity. We see that aging causes a decrease in the microstructural integrity of the brain. Okay. So, how do we measure the microstructural integrity of the brain? That's one thing that we're going to talk about. But I also want to talk about how we measure fitness in these individuals. So we capture cardiorespiratory fitness, and this is where you all come in. You're going to be really familiar with one of these slides that I actually present on. So measuring cardiorespiratory fitness. So everybody here has probably seen this graph at some point, but this is typically how Dr. Clayson and I did it. We worked with a cardiologist, Dr. Allison Bailey, who's unfortunately no longer at the university, and we collected this data over at the CCTS. But essentially, we had the individuals running on the treadmill, and we have exercise intensity on the x-axis and then oxygen consumption on the y-axis, right? And so typically, in any max GXT or an graded exercise test where you're trying to push somebody to peak or max, you're going to increase the intensity, whether that be with speed or by increasing the grade. And then you're going to see an increase in oxygen consumption, right? So you all had all of this before. So you take them up to the next level, you'll increase the intensity, and you'll see an increase in oxygen consumption. But as you all know, at some point, after you increase the intensity, you're going to see this plateau, right? And so that's what we would typically define as VO2 max. But it's really hard to push somebody to that particular point, especially if they're 60, 65, right? So typically, what we would end up seeing is they would give us a thumbs down before they reached a plateau, all right? So at this point, you gotta ask yourself, is this person quitting just because they don't feel like doing this anymore, or are they actually working hard physiologically, right? So how do you define VO2 peak? And so what we decided to do is set secondary criteria. So again, we did not see a plateau in a lot of our subjects. So we set secondary criteria to ensure that these individuals are working hard, right? So they have a respiratory quotient of greater than or equal to 1.1, achieve an age-predicted maximum heart rate using 220 minus your age. Does anybody know the history behind 220 minus your age? So I think Fox is the person that published this. And, I can't remember how many subjects were in this paper, but the author just said, well, it looks like 220 minus the age is the appropriate equation. And so we've just kind of generally accepted that. We know now, though, that these can be gender specific. So it's kind of interesting to kind of look into the history of these things. It's just like the equation really wasn't calculated. It was just like, oh, that slope looks like it's about 220 minus your age. And then they had to have a rate of perceived exertion of greater than or equal to 17. So we tried to guarantee that they were working hard. Otherwise, if stage 2, if they give us a thumbs down, you can't count that as VO2 peak because they're physiologically they probably weren't working that hard. So that's how we captured cardiorespiratory fitness. And I do want to kind of highlight the fact that we used a standard protocol across everybody, and that actually turns out to be advantageous because you can actually look at total treadmill time. Total treadmill time was a strong predictor of some of the measurements that we're looking at. So instead of starting at a certain level based on the person's fitness level, we decided to use a standard protocol across everybody. All right, so as I mentioned, microstructural changes occur with aging as well. We see a decrease in microstructural integrity of the brain. So how do we measure white matter microstructure with MRI? So we use diffusion tensor imaging, and it allows us to kind of look at the rate and the directionality of water diffusion in the brain. So we're actually able to look at the microstructural integrity of the brain without actually being able to physically see it. We just look at the diffusion of water. So what I've done here is I'm illustrating this by these two different environments on the left and on the right. So on the left we have a droplet of water in some environment, or black ink, let's say. And on the right we have the same droplet of water in a different environment. So I'm going to start this animation, and I want you all just to kind of take note to the difference in pattern that you see in the diffusion of these water molecules over time. Right? So if you just look at these diffusion patterns, it's going to tell you about the underlying structure, even though you can't actually see it. So here we go. So these are just diffusing water molecules over time. And what you can see here is it looks like on the left, water diffusion is kind of equal in all directions. Okay, imagine this is a three-dimensional space. Whereas on the right, it looks like something is inhibiting this water from diffusing horizontally. Okay, so it has more of a directional component to it along the vertical axis. All right, so this tells us information about where we are in the brain just by looking at water diffusion. So on the left, this is called an isotropic environment, so iso being the same. So the diffusion of water in the ventricles is usually spherical in shape. Whereas if we're in a bundle of axons, so think about a handful of straws, okay? We're in a bundle of axons, water diffusion is going to be greater along the longitudinal axis of those straws versus the perpendicular axis, because the plastic in those straws is preventing the water from moving perpendicular. So axons are fairly similar in that manner. And so what we can do is we can calculate this ratio called fractional anisotropy, where we end up with this arbitrary value between 0 and 1. So 0 would represent a perfect sphere, and the value of 1 would represent a really thin cigar or a really thin straw. And so what we do is we can assign geometric shapes within our three-dimensional pixels, which we call voxels. So after collecting or looking at the white matter or looking at the water diffusion in each pixel or each voxel, we can assign a shape to that particular voxel. So using those two techniques, so we assess cardiorespiratory fitness using a treadmill test, and then we had these participants come to the MRI machine and we scan them to look at the white matter microstructure of the brain. So what is that relationship that we found? And this was during the dissertation. This is part of my dissertation. So what I'm going to do is I'm going to show you some results of what we found, but I'm going to kind of orient you to how we represent these in figures in publications. So what you're looking at here is a template of the brain that's being, you can download these free software programs that already have these templates loaded up. And you're looking at, again, a sagittal slice on the top, one from the left, one from the right. This particular image here is a transverse slice, so you're cutting through the head this way. And then this particular image is a coronal slice where you're cutting superior to inferior, you're looking on. Now what you see in green is just a white matter skeleton. So again, the software that I mentioned that you can download will actually calculate the average average white matter tracks in all of your participants. Okay, and it creates this skeleton to show where the white matter resides within the brain. So what we do is we perform our statistics within this skeleton, and we can place it on the template to allow people to kind of visualize where we see these relationships. And this is what we see. So we see that cardiorespiratory fitness was positively related to white matter integrity in portions of what's called the corpus callosum. The corpus callosum is this major white matter tract that connects your right and left hemispheres. Now, what's interesting about this is that this relationship is the cardiorespiratory fitness value that we used to explore this relationship was a combination, it was a composite score of VO2 peak, using those criteria that we already talked about, total time on treadmill, again, it was that standard protocol, and 1 minute heart rate recovery. So how fast did your heart rate recover within that first minute after exercise? So it was a composite score of cardiorespiratory fitness. And then we controlled for age, sex, and socioeconomic status. So again, positive relationship. It's just correlational, but interesting relationship. And these are a couple graphs. So if we looked at a regression analysis and we were trying to determine which two of the three variables that we use in the composite score best predicted these values of white matter integrity in the brain, this is what we saw. VO2 peak and total time on treadmill were strongly related to this fractional anisotropy value. And this was an interesting finding in my opinion, but we wanted to take it a step further. So as I mentioned, this software that we can use allows us to place these geometric shapes in every single voxel. And so what we can do with that information is we can say, okay, in the brain where we see this relationship, where do those fibers go? What regions of the brain do those axons connect in the left and right hemisphere? And so this is a video of that same region. So here's that corpus callosum connecting the left and right hemisphere. And then these are fibers. I'm going to actually rotate this around. These are fibers connecting both hemispheres. And this makes this a nice video for a presentation. I always laugh because I present on this technique, and people think it's interesting, but I really appreciate the amount of work that went into actually developing this technique. I mean, I'm just an end user. The people that came up with this stuff are much smarter than I am. But these are the fibers that are connecting each side of the brain, where we see that relationship. And the color here is just denoting which direction they're running. So red is running left to right, right to left. Blue is running up and down, and then green is running from the back side of your head to the front side of your head, back and forth this way. So because it gives us the ability to do that, we wanted to ask, well, does it make sense that we see this relationship between cardiorespiratory fitness and white matter microstructure in this particular part of the brain? And so what we did was we used this same software program to ask, okay, here are those voxels that show this relationship between cardiorespiratory fitness and white matter health. And then we told the software, said here are 6 anatomical sites that we know are probably interconnected in this portion of the corpus callosum, because we know the brain is organized, so we knew the anatomy. So we said, okay, of these 6 regions, where do these particular axons within these voxels project? Right? These are the 6 regions that we decided to use. So these frontal regions here are heavy in cognition. Premotor cortex, obviously heavy in motor. Precentral gyrus, postcentral gyrus, primary motor cortex here, and this is the primary sensory cortex. And so this is what we see. So this is a single representative subject here on the left. And so what I've done is, so this software program will actually spit out or tell me which region these particular voxels are projecting to. And I've color-coded that according to what region it was projecting to. And this, if anything, just validates the software program. So if we zoom in on this, as I said, the brain is highly organized. So the more anterior regions of the corpus callosum are projecting to more anterior regions of the cortex. And as we move posteriorly, see how it follows the pattern of the targets that we selected? So this just highlights the validity or the capability of the software program that we're using. And it tells us, yes, that the brain is highly organized. But what we see is most of the voxels are projecting to premotor regions. Okay, so motor regions. So we didn't collect any information on how much these people exercise. So one thing that I'm going to do in this presentation, I think I'm going to start to do more and more often, especially when I'm talking to students, is talk about the mistakes that I made. Because, we get up here and we talk about, oh, these are lovely findings, but you all need to know that we make mistakes, or I make mistakes all the time. I speak for everybody, and then it's okay. Just you try to do some, you try to improve on the next study that we do. So we didn't collect any information on how much exercise these people participated in prior to the study. But this tells us, you can imagine, if we see this relationship as your cardiorespiratory fitness goes up, your white matter integrity goes up in this region. You can imagine that those individuals with a higher cardiorespiratory fitness probably exercise more than those that have the lower cardiorespiratory fitness, but we don't know, because we didn't collect that information. It would have been important to know. But this just kind of highlights the fact that, oh, you would expect if a person's exercising more, that they're moving their limbs more, that this portion of the brain might be connected, more highly connected than compared to other regions. So, dissertation, this is what we found. Dr. Clayson was on my committee, and we published on this. So we see this positive relationship between cardiorespiratory fitness and white matter microstructure. Now, we want to ask the question, what are some of these underlying mechanisms? And this is still something that hasn't been answered. This is still something that a lot of people are looking at. But as you can imagine, just from an MRI technique and a research standpoint, we're pretty limited on how much we can look at in the brain at this point without being invasive. Okay? Well, let's talk about some of the underlying mechanisms that have been proposed. So, animal models suggest that cardiorespiratory fitness benefits from brain health in part by vascular changes, as you all can imagine. Better vascular health of the brain is going to improve the health of the brain. But less, at the time, less was known about the relationship between cardiorespiratory fitness and cerebral blood flow in humans. So this last image was done in rat and mouse. And then not many people at this particular time, so this is 2011, 2012, had done this in humans, or looked at this in humans. But that's just because it's, to look at cerebral blood flow, it would be highly invasive if we want to try to quantify CBF in humans. So what we decided to do, once we established the fact that we could actually look at this non-invasively through MRI, is we started to use an MRI technique that allows us to look at blood flow to the brain. Before I talk about that though, I'm going to talk about this relationship between blood vessel health and white matter microstructure. So we're thinking there's this vascular relationship, and actually out of these slides, I started to transition into my cerebral blood flow talk. But I added these slides this morning because this highlights the reproducibility of what we're looking at. So looking at blood vessel health is one thing that can give us more information about this relationship between brain health and exercise. So we're going to take a look at this video here that kind of highlights the importance of endothelial function, and hopefully you all can hear. Can't hear it, but is there an audio? If not, it's fine.
The health of a person's vascular system reflects a wide range of sophisticated biological and physiological processes regulated by the endothelium, which is considered to be a superorgan with endocrine-like properties. Endothelium dysfunction is the most common form of vascular abnormality and the earliest clinically detectable marker of vascular health. It is now evident that endothelial dysfunction is treatable and even reversible with optimal medical treatment, titration of medicine, and lifestyle modifications. Vascular health is an expression of the cardiovascular system's focusing on the performance of the small vessels, which correlates with various biological and physiological effects. Among them, 6 key processes known as biopac: vasodilation, inflammation, oxidation, proliferation, angiogenesis, and coagulation that ensure homeostasis.
So we've had a machine donated to us that allows us to look at this vasodilation aspect of blood vessels, looking at endothelial health. And it's called
The health of a
the EndoPAT. I don't know if anybody has heard of this, or Joey, have you talked about it at all?
No, we haven't.
Okay. So this is kind of a representation of typically of what we do and what you're looking at here, you kind of get assessing how compliant or how flexible your arteries are, okay? And as you saw in the video, this is an early indicator of vascular health. So what you do with this machine, you put these probes on an individual's finger, and you inflate this balloon here, and you kind of measure the pressure at the fingertip, all right? And that's going to be based on how much blood is going in the fingertip. So let's watch this video, and it kind of gives an example of how we are able to calculate this measure of endothelial function, or what's called reactive hyperemia index. So we measure it baseline here, baseline blood flow. Then we temporarily restrict blood flow for about 5 minutes, and then we look for an increased response after that occlusion. Okay, so you can imagine if your post-occlusion amplitude is equivalent to baseline, you didn't change that much. Your vessel isn't very flexible, but if it can open up a significantly greater amount, then you're going to see a huge gain post-occlusion. So that tells you that your vessel's compliant and it's healthy. Okay, so it's going to give you a higher index. And so we use this index to look at this relationship between, again, white matter microstructure and blood vessel health. And so, again, looks similar. So this is in a completely different group of older adults. All right? And we see this relationship between blood vessel health, so this reactive hyperemia index, and fractional anisotropy. So as your index goes up, blood vessel health goes up, your white matter integrity in a very similar region of the corpus callosum goes up, slightly more anterior. Now, it's more anterior if you think back to those target regions that we selected. More anterior regions are more associated with cognitive function. So what we wanted to look at is this relationship between cognitive function. But before we do that, what we did is we tracked these fibers again to the cortex, and now what we're seeing is this particular region of the brain is now connecting, as I mentioned, frontal polar cortex and superior frontal gyrus. Again, they're associated with cognitive function. So we had some tests to look at cognitive function in these individuals, and it's called the trail making test. So trail A, so it's essentially connect the dots. So you have 1 through, let's say, 15 randomly sorted on a piece of paper, and you tell the person start at 1 and they connect the dots in sequential order, 1, 2, 3, 4, 5. Okay. Then trail B, what we do is we tell them to alternate between numbers and letters. So there's more of a cognitive component to it. So they have to go 1A, 2B, 3C. So they have to switch back and forth when they're doing this same task. And so what we do is we just subtract trail B minus trail A. And the greater the difference there, that's typically associated with a lower cognitive function. So it's harder for them to do trail B compared to trail A, then they're performing at a lower cognitive level compared to somebody else where there's a small difference there. And so this is what we see. We see this relationship between reactive hyperemia. So as that goes up, this difference goes down. And then we see a relationship between the white matter microstructure in this region and our executive function measure. We call it executive function when we administer this test. So again, this was in a completely different group of individuals. So we know something's going on potentially at the vascular level. So this is one thing that I have on my door just to kind of remind me to get to the gym, right? What fits your busy schedule better, exercising 1 hour a day or being in bed 24 hours a day? So true. And again, think about how do we motivate people to exercise? So as I started to talk about cerebral blood flow, the biggest problem with this historically has been how do we measure this in humans non-invasively? And we are now able to do that using MRI. And so we're going to talk about that in the next slide here. So we use this technique called arterial spin labeling, which allows us to do this. And so imagine here on the left and right side of the screen, you have 2 conduit arteries, so you have your carotids here. And when the person's in the scanner, we put them supine in the scanner, and the magnetic field is kind of facing towards the top of their head. And once we put somebody in, that magnetic field is so strong that all of your protons are going to point in that same direction in the main magnetic field. And so you can imagine as your blood is flowing up to your brain, if we label all of the protons in your blood, they're all going to be pointing in one direction as they head to your brain. And then we can take pictures of your brain at that particular point in time. And that gives us some type of grayscale value. Again, these are three-dimensional pixels or voxels. Now, what we do with our serial spin labeling is, at the neck, we can actually, these are called untagged voxels. And at the neck, what we can actually do is administer a radio frequency pulse to flip these protons 180 degrees as the blood is coming up to the brain. So here's essentially what happens. You've got the blood coming in, we apply a pulse here, and then they invert their orientation. And then we take pictures again at that same level of the brain. Now, what you've noticed is the voxels now in the same region are darker. That's because as these protons get to the brain, some of them start to recover and return to the strength of the magnetic field. Some of them don't. So we lose signal when we take a picture of the brain here. And we call those tagged voxels. And then we can simply subtract those out, and we get this different grayscale intensity. And depending on the amount of blood flow you have to certain regions, we can label it with a hot, cool type map. And obviously we can quantify those. So we can use this technique now to say, okay, what is that relationship between cardiorespiratory fitness and blood flow? And this is a region called the default mode network here. And what we're doing here, this is that fitness composite again. So cardiorespiratory fitness in this particular study, since the first study we found this relationship between total time on treadmill and VO2 peak. Those were the best predictors of white matter integrity in the brain. We decided to use those solely as a composite in this particular study. And we looked to see what is the relationship between cardiorespiratory fitness and cerebral blood flow in what's called the default mode network of the brain. And we see this positive relationship. Now, what I want to do though is highlight the importance of the default mode network. So here we have kind of a lateral view of the brain. Again, you're looking at the left side here, and we take my left hemisphere off, and you're looking at the midline of the right side. And the default mode network is this region. Some people describe it as this internal monologue. So I like to talk to, when I'm teaching to my students, the way I like to talk about the default mode network is when you're listening to me, you're outside of your default mode network. When you're attending to what I'm saying or a video or animation on my screen, you're not using your default mode network. Once you start to kind of go back into yourself and you start thinking, oh, well, I've got a test today, it's Friday, I don't really want to be here for this seminar, I can't believe I got up this early, what am I going to do the rest of the day? You start thinking about stuff in your head, that's the default mode network. But it's also important for memory retrieval, like I said, self-referential thought processes. Okay? But what makes it most important, at least more recently, is that this is where we see a lot of AD or Alzheimer's disease pathology in the brain. This is where it starts. So what I'm doing here, this is just an activation map showing where the default mode network is. And if we look at a map of where AD pathology resides, so I'll go back to the default mode network here. And then this is an overlay of typically what we see where AD pathology starts. We see a nice overlap between the default mode network and AD pathology. So then if we could put the medial aspect, medial view of DMN versus where we see AD pathology, quite a bit of overlap. So we think there is a vascular component to AD that exacerbates some of the tau protein and A-betas that accumulate in this particular region of the brain. But what we're seeing is, if we go back to what I just showed you, we're seeing that the higher your cardiorespiratory fitness, the better the blood flow to this particular region. So that could be neuroprotective. But again, it's just a correlation. So we're just seeing correlations. So we see that cerebral blood flow shows a positive relationship in the default mode network with cerebral blood flow. So part of the same study, Dr. Clacy and I recruited a couple cardiologists, and we were really curious about heart function and how that's related to cerebral blood flow to this same region of the brain. As we all know, as we get older, the heart takes a hit just like everything else. So what about, can we look at myocardial mechanics and this relationship between two cerebral blood flow? And so how do we measure myocardial mechanics? Again, this is where we brought in our collaborators. Unfortunately, Dr. Bailey's no longer at the university, but Dr. Vedant Gupta and Steve Leung are still here. And so what they did is they performed echocardiograms, ultrasound of the heart, for us in all these participants. And we were able to measure something called global longitudinal strain, which is just basically the percentage of shortening relative to the original length at rest of the heart muscle. So this is an example of an echo, and then on this side you can see what they do is they look at how short does this get relative to the original length. So you can imagine the shorter it gets, the greater the ability to push blood out of the ventricle is. And so again, what we see is we see this positive relationship between global longitudinal strain and CBF in the default mode network. So again, cardiorespiratory fitness and brain health, we see heart function is related to CBF, to the default mode network. So in summary, we see that, again, a lot of this has been correlational. I've got one study that was published where we see this relationship with cognition, but we do see that fitness is related to white matter microstructure in brain regions connecting motor areas, which we might expect, and blood flow to the default mode network, which is an important network that's related to Alzheimer's disease. And we see that vascular health, by using the endopat technique or looking at endothelial function, is also related to white matter microstructure and cognition. And then myocardial function is related to default mode network blood flow as well. So again, correlational. So my next question is, how do I establish a causal relationship, right? So these are great, we're seeing all these correlations, but how do I establish a cause and effect? And this is another slide, I love this, just used to stare. So Dr. Clacy mentioned the K Award, and so this is part of where I want to highlight some of the mistakes that I've made. The K Award design was set up like this, okay? And what I decided to do, instead of having a control group, I wanted to eliminate the human variability. I was like, oh yeah, I'm going to eliminate variability across groups. I'm going to use the same participants for the entire study. So I'm going to bring them in, collect a baseline measurement. They're going to stretch non-aerobic exercise intervention for 5 weeks. We'll measure everything again post-stretching. So we're collecting fitness measures, we're collecting MRI data, we're collecting cognitive data. And as you all might expect, you might not see a change here, right? Because we're not impacting cardiorespiratory aspect of fitness. Then what we'll do is we'll train them for 3 months aerobically, 3 times a week. They'll come in, we'll do some high intensity training, which we did. A couple problems though. So you might notice 5 weeks here versus 3 months here, all right? Now, that's a different amount of total time, but the time equated, the time of exercise was equivalent. Okay, so the total time that they exercised in 5 weeks was equivalent to the total time they exercised in 3 months. That's not that big of a deal, but it can have an impact on the changes that you're hoping to see, because the time alone could impact some of these measurements. The other aspect about this is I'm measuring cognition here, here, and here without a control group. That's problematic because if you see the same cognitive test 3 times, you're probably going to improve by the time you get to the 3rd time. So there's no way for me to account for practice effects in this design because I didn't have a control group. Okay, yeah, it's great to eliminate that variability from 2 different groups, but without a control group, I can't naturally say, okay, well, this is how much they improved just by seeing the cognitive test 3 different times. Now, what I can do is look at structural changes, because that's not gonna change, you know, we're not gonna see a practice effect on CVF, white matter microstructure. So I can look at some of these structural changes, but when it comes to behavior, I've pretty much done myself in. So now I need, for my next study, it's gonna have to be two separate groups.
Yeah, I was just wondering if you saw an actual difference, then that could have been a training effect between baseline and then the pulse stretching measurement that could have indicated that there was a training effect.
Yeah, so very small, no significant change. So that's one thing that I can look at. I can look at the behavior. Is there an improvement from here to here? But a reviewer is still gonna say, well, they've seen it twice already. So how do you know that it's not just a practice effect issue? And that we're in the process of still analyzing all of this data. So these are the markers. So one thing, we have a driving simulator on campus. So one thing that we want to look at is driving performance and attention. Because who hasn't been out on the road and say that old person's tested it? So, and it's funny because some of these participants ask us, are you going to send this information to my insurance company? Like, no, this is private information, we're not gonna send- or family. So we're dealing with that right now. My grandfather's 94 and we're trying to get his license from him. He doesn't like it. And the other thing that we collected is blood markers. So we want to look at inflammatory markers as well. Those are, I just don't have money right now. Those are sitting in a freezer. I'm looking for somebody that actually has money so we can actually do some of these analyses. But this particular, as I mentioned, some of these markers, it doesn't matter that, you know, we're doing this 3 times. What I'm really curious to see is if we see any changes in some of these blood markers here. But again, that takes me back to this 5 weeks versus 3 weeks. If these were equated through time, then this would be a little bit better design. So keep that in mind when you're designing studies, if anybody's planning on going into research. So these are the acknowledgements. So as I mentioned, Dr. Bailey worked with us. Of course, Jody was part of the team. David Powell is one of the physicists over at the MRI Center. If you're interested in doing any imaging research, did a lot of these people meet Dave when they went to the MRI Center? Or no?
People that had 600, KHP 600,
Okay.
met Dave,
If-
so
if-
part of it.
Yeah, if anybody's interested in doing imaging, this is the guy to talk to. Doug Long is Dr. Facey's former grad student who now works over in the College of Health Sciences. And of course, funding, and this is my previous mentor here on campus, Dr. Brian Golden, some of his people in his lab. So that's where we're at now. Right now, it's kind of tough to get money. It's funny that Dr. Facey told me, or was talking about going back to get the PhD. I came back to get the PhD primarily to teach. It just kind of fell into this research aspect of things. But right now, it's difficult. It's been difficult for me to actually get money. But we're looking, obviously, to do another intervention study where I'm actually have one control group and one therapeutic intervention group. So to kind of improve on the mistakes that I've made in the past that happens. All right, how are we on time? Okay. Anybody have any questions? I just want to get out of here.
One of the questions I have, you were talking about the last slide, maybe 2 slides ago. The group, you don't have, you said it's a big problem, but you don't have a control group test like familiarization
Practice,
against.
yeah.
Why couldn't you just go back now? All you would need to do is just recruit
Yeah, so,
people who meet your inclusion criteria
Right.
and test them 3 times. It seems,
yeah, I can certainly do that. Part of the issue is money,
okay.
and then part of the issue is time. So,
Yeah.
because I don't have a grant now, I'm teaching more. So there's this balance between teaching and research. So, and then obviously I have to pay people to come in, but yeah, that's one thing that we talked about doing if we get some money. So,
I think you're eliminating that.
yeah, yeah.
Yeah, I kind of, to go with that, I was wondering if you could just go back to your IRB with the other study and ask if you can contact the subject again and give them a questionnaire of their physical activity, and they could also have that.
Yeah, well, the nice thing is, this most recent study, the IRB is still open on it, so we could potentially do some of this. The other one's closed, unfortunately. And the other thing that we have to consider is making sure, so anytime you give a survey and you ask somebody to recount how physically active they are, there's a whole host of issues with that. But then if you're asking, so that study was done in 2012, it'd be hard to ask them, how active were you? Like, I don't remember what I was cycling a lessons to take away if anybody here is actually interested in research in the future. So,
But this most recent study got physical activity.
yes. Yeah. So that's one thing that we opted to do, because the first one we didn't collect it, was we gave everybody Fitbits for a week. And we just said, go about your normal activity level, and so we could account for how much activity they, yeah. And then they're at jalapenos doing this. So,